Okay, everybody, we're going to get going here soon. I just want to introduce myself. I'm Matt Baldwin. I'm going to be your track host today. Thank you for coming out to Building a Medical AI with Kubernetes and Kubeflow by Jeremie Vallee, who's an infrastructure lead at Babylon Health. After the session, I want to encourage you to go to the schedule app. Please rate the session. If there's any questions, I ask, please hold those to the end. We're going to leave some time. And I'm going to come around with a microphone and let you ask the question through the mic. So if you can wait to ask the question so I can get you with the mic, please do so. With that, hand it over to you.
Hi, everyone. Thank you for coming to this session. Today, I'm going to talk about a transformation from running a set of training jobs and Jupyter notebooks and all other AI workloads on bare metal servers to running them in a cloud platform on top of Kubernetes in a multi-region way and actually a multi-cloud way. But it's happening in the context of healthcare, and it comes with different other requirements. So my name is Jeremie. I work for a company called Babylon Health, and our mission is to provide an affordable and accessible health service in the hands of everyone on Earth, which is a big mission, and it comes down to two main challenges. The first one is accessibility, and the second one is affordability. So for tackling the accessibility problem, we have to look at what can we do to bring people closer to healthcare professionals. And what we did in 2014 is we launched a product that would allow you to get a digital consultation with a doctor from your mobile phone. And so you could have a video or an audio consultation. And it's been 5 years now, and we reached over 2 million digital consultations. So the service has gotten a lot of traction and is working well. But then comes the problem of affordability. Accessing healthcare professionals is expensive. And actually, according to the World Health Organization, we actually have a shortage of about 5 million healthcare professionals in the world. So it becomes a very hard problem to scale, accessing healthcare professionals. But there is something that we all know is easy to scale and getting cheaper and cheaper every year, and that is a computer. So to work on the affordability issue, we started thinking, what if we could use computing technology to bring some of the services that you would usually get from a healthcare professional, and also serving it from a device that most people have, which in this case is a mobile phone. And so we created different sets of products that kind of help you get started with managing your health. We have, for example, a symptom checker when you can tell the app if you have a headache, for example, and then the app will try to understand what's going on. We also have a product called a digital twin, where you assess your whole body health and mental health, and you can actually see a representation of yourself and try to see where you can work on improving some of your conditions. All of this requires different type of technologies, and we're working on things like NLP, computer vision. We also do Bayesian networks and all sorts of other products. And that means a lot of research and a lot of compute. So I'm going to tell a bit about how this all started in our company. About 15 months ago, I had a discussion with researchers at Babylon, and they had built a graph-based neural network, and they were running hyperparameter tuning on our on-premise servers. And they wanted to improve the efficiency of our models. But it became quite clear that we not only didn't have enough compute to run this hyperparameter tuning, we also didn't have the orchestration to make that happen. It's actually very complex to orchestrate hyperparameter search, especially when you're on-prem like this, like we were. And at the same time, our company just had migrated all of our workloads to Kubernetes. So we thought, all right, let's try to run this experiment on a Kubernetes cluster. But we're missing one piece where we needed a way to orchestrate the hyperparameter tuning. And we found a tool called Kubeflow. Kubeflow is a machine learning toolkit for Kubernetes. And it has one of its components is a component called Katib that does exactly hyperparameter tuning orchestration. So with combining the two, we wanted to get started and see if it would work. So we deployed a cluster. We deployed Kubeflow on top of that. And what we did is we took our scripts and Dockerized them. And we sent them to the servers to run. We ran about 50 nodes for a week. And that resulted in 1,600 CPUs, over 3 terabytes of RAM. So much more compute than we had locally. And it actually it was a really good success for us. We managed to get good results. And the team published a paper that used this experiment as the experimental setup of their theory. And at the same time, our company was growing. We were onboarding more and more teams doing AI models. And we wanted to find a way to make these teams more efficient. So we started looking at how can we do to maybe centralize all of the things that gravitates around machine learning. So how do we manage infrastructure? How do we manage our models? And so we thought of this idea of having a platform where you could take from an idea to production very easily via experimenting, training, tuning your model, validating your model. I'll talk about it a bit later in details, and then deliver them to production. But we had to think about being in the context of healthcare and trying to understand what does it mean to do this in the context of healthcare. So the first thing that comes to mind, obviously, is security. But also, we wanted a good auditing solution, so a way to find exactly what happened on the platform and for what reason. And also, another important thing was safety. We wanted all of our models that get produced by this platform and produced by Babylon in general to be safe once they reach production. Another thing that we wanted to keep in mind is that working in healthcare and deploying your stack in different countries you operate, you have to think about where the data is. And most of the times, the data will need to stay in the country you will deploy your solutions. So we wanted a way to have a platform which is flexible enough to be deployed on any type of infrastructure, whether it's cloud or on-premise, anywhere in the world. So running Kubernetes was quite convenient. OK, so what I'm going to talk about today is how we are building this platform. And I'll have 3 different parts. The first part is how we are building the base of the platform, and then how we manage the workloads on this platform. I'll talk about a bit the use cases that we have and what we are planning for the future. And my hope here today is that I can show you that using open source technologies and technologies that you can find in the cloud native world can help you also build your own platform if you need to. OK, so let's start with the base. It all starts with the infrastructure itself. There are a few things to keep in mind where you're building a machine learning platform. The first thing is you actually have to manage, you have to prepare for different type of workloads. Some teams are going to need GPU nodes. Some other teams will need CPU-intensive nodes. So you have to make sure that you're prepared for all of this. And so where you're running in a cloud environment, you can use auto-scaling groups. So make sure that you prepare different type of nodes for that. We currently use 6 different types of nodes at Babylon. Now, another thing to keep in mind is you want to make everything that you have in that cluster private. Some clusters, by default, will have a public Kubernetes API. I really recommend you to make it private. And same thing goes for the nodes. We run all of our nodes in private subnets, and the access is very restricted. We also encrypt all of our nodes. And depending on the cloud provider that you're going to use, you'll see that sometimes it comes for free, and you don't have to do anything. If you're using AWS, one thing that we found out is you must encrypt your EBS volumes if you want encryption at rest, but also make sure that if you want your root volumes to be encrypted, you need to encrypt the AMIs before deploying them. And for this, we use Packer. So we prepare all of our nodes using Packer. We harden the nodes, and then we encrypt them, and then these AMIs get encrypted. If you run a Kubernetes pod on those nodes and you haven't encrypted the AMI, then the root volume might be used for the Docker volume, and so you wouldn't be running on an encrypted volume. So keep that in mind. We also want to use OPA as an admission controller, and that allows you to kind of like filter some errors that could be sent by users, such as forgetting to put a label. So OPA could actually block the request to create a pod and say, no, this label must be here. Or, for example, blocking different CPU requests. And you want to enable Kubernetes audit logs, which is very important to know exactly what happened. You can find all the events that happened during during your workloads. After you have the Kubernetes cluster, you want to bootstrap it. And so for this, we use the GitOps methodology. We deploy everything on that cluster using GitOps. The tool that we chose for this is Flux. And Flux is a tool that will listen to changes on the GitHub repo. And once the change happens, it will pull the latest information and apply this in your cluster. There's a few examples of things that we deploy right here. What's really good with that is that we can use GitHub as the source of truth of everything that happens in the cluster. It's very good for auditing as well, and you can see who decided to, for example, upgrade Istio at 2 a.m. in the morning for some reason. It really reduces human error, so we don't have to operate the cluster ourselves anymore. We let Flux apply all of the changes. All right, another thing that you want to configure and secure is your networking layer on Kubernetes. We wanted a way to provide a zero trust policy, which means that we didn't want a service to be able to reach another service without having us configuring that specifically. We also wanted a way to encrypt communication between services and perform mutual TLS. That's something that we always wanted to do, but there's actually some regulations in healthcare, like HIPAA, for example, that ask you to encrypt your traffic between services. So that was also quite convenient. And for all of this, we decided to go with Istio, mostly because our current platform is also using Istio, and it fits all of the challenges that we wanted to tackle. Here I put an example of a configuration that would allow service A to talk to service C. So you create a service role that allows calls to service C to go, and then you bind it to the service account of service A. And you can do all kind of different configuration on this. You can, for example, if you need to restrict access to the internet, you can use Istio to help you with that. There's other configuration to keep in mind, though. OK, let's talk about cluster management. So at first, we had to think about how would we structure everything that runs on a Kubernetes cluster. So we decided to come with the name of a project. Everything that will run, everything that our users will run on the platform will be a project. And that project will be isolated from other projects so that you wouldn't actually be sharing resources directly. We also wanted to enable collaboration. So we wanted people to be able to share their projects with others if they wanted to. And we wanted every project to come up with a volume that they could store results, models, data sets on. And we wanted that volume to be accessible from any pod within that project. For this, we arrived with a NFS-like solution where you can actually attach as many pods as you want to the same volume. So if you're running distributed workloads, they could all be writing to the same folder, for example, which is quite convenient. So we created a project custom resource on Kubernetes and an operator. So every time a user would create a project, we would set up a namespace, some RBAC rules, and the persistent volume partition. A bit later, I'll talk about Kubeflow in a minute, but a bit later we saw that Kubeflow introduced this notion of profile, which is very similar to what we called a project before. So we re-architected that to include the Kubeflow profile notion. OK, so let's talk a bit about Kubeflow. Kubeflow is the machine learning toolkit for Kubernetes, and it comes with many different components. You can see them on the screen right now. And what we really love about Kubeflow is that it's very modular. So you can actually decide what you want to install, and then based on your needs, then you can deploy them. So here I gave some examples of what we use with Kubeflow. I talked about Katib earlier. We're also a big fan of notebooks, so we use the Jupyter Notebook controller. We have TensorFlow training jobs and PyTorch jobs as well. And we started using Argo workflows for some of the use case. Actually, one use case I'll talk about later. But all of this is deployed, again, with the same GitOps methodology. About a few months ago, Kubeflow moved all of its deployment tools to customize. So you can easily play with customize, generate a big YAML configuration, push that to your GitHub branch, and have a tool like Flux deploy that automatically. You can also use other tools for CD, like Argo CD, which is a good one. And since 0.6, which came out this summer, Kubeflow is multi-user, which means that you can access and control the access to some of the UIs of Kubeflow, like Jupyter Notebooks, for several people. And this is an example of how it works under the hood. There's been a talk already at KubeCon about this, so I won't go into too many details. But the idea is when a request goes through a load balancer, we have an Envoy filter that will redirect the traffic to the Kubeflow auth service. And then you can integrate it with your IDP. I put Dex here. It's an open source one. We use our third-party one, and it works great. And so once you're authenticated, the Kubeflow auth service will inject a header into the call that will then get to the Kubeflow gateway and will redirect it to the Jupyter notebook that you're trying to access. And then you can use Istio RBAC rules to actually block or not the access to a UI based on who you actually are. Another part that we had to think about is how do we access data and how do we configure secrets on the platform. At Babylon, we have a specific team that's dedicated to providing access to data sets, and they built an access layer, and we integrate with that layer from our platform. But the idea and what you want to keep in mind is that you really want to audit who gets access to the data, and that's really what we wanted to do. Every time a user wants to access data, we want to know for what reason, for what particular project, who will be using it, and so we want to control that all the time. Another big thing to keep in mind when you have a lot of data is you need to enable your users to see what data you have, and for this, there is a discoverability tool called Amundsen, which is open source. I really encourage you to check it out. That just allows you to browse and see what kind of data set you have in your system. And then for secrets, well, it's pretty straightforward, but use a secret manager like Vault. We use Vault. We're very happy with that. And one thing that you can do with Vault is you can make your pods authenticate to Vault directly to fetch secrets and load them in memory, which prevents you from actually writing a secret to a Kubernetes secret, which is base64, so not the best security. OK, this is actually pretty important. When we created the platform, very early on, we had users telling us, OK, I want to see exactly what's going on. I want to see how my training job is doing. So we need to find a way to collect all of the metrics that was running on the cluster. And we also wanted for people like me, like more on the MLOps side, we wanted to know how the cluster was doing. And for this, we went with a very obvious solution, which is Prometheus, to collect the metrics of our clusters, and Grafana to visualize them. What's really good with Grafana is that you can automate your dashboards quite easily. So this is an example of a dashboard that we provide to our users, and every single project that gets created gets its own dashboard on Grafana, so people can follow. And we add more and more monitoring and metrics after that. And we also want people to expose metrics during their jobs so that if they want to build custom dashboards, they can. A few lessons that we learned are if you want to use Grafana and you want to deploy it on a Kubernetes cluster, there's a Helm chart for this, and it is quite convenient. Every single dashboard can be applied as a config map. So if you apply a new dashboard via config map, Grafana will automatically load the dashboard into the UI, so you don't have to restart anything. And you can then just put the config map part of the GitOps again and get it applied automatically. If you have multiple Kubernetes clusters like we do, you can use the federation feature of Prometheus, where you have one central Prometheus that's pulling the metrics from all the other Prometheus, and then you can visualize them in one place. And if you're getting too many metrics and you're spending too much on storage or Prometheus doesn't scale, then you can check out Thanos, which is a distributed storage solution for Prometheus. So you might have seen this in the first slides about monitoring, but one thing that came out also very quickly when people started using the platform, they wanted to understand how much they were going to spend. So again, keeping in mind this was running on the cloud, and everyone was actually asking us, OK, but like, is it going to be expensive? Like, I need to know. So we tried to find a way to expose, like you can see here, expose the cost of every research project. And we tried to look around for open source tools, and there's actually not a lot of them. We found one which is a third-party tool, but open source their cost model called KubeCost. And you can check it out. It actually exposes the metrics to Prometheus. We were already using our third-party tool, so what we did is we built a small Go app that will ping the API of that tool to get the cost per namespace, which is the same as the cost per project for us. And then we were just exposing it as another metrics in Prometheus. which means that now we could expose the project costs per project. OK, so taking a break here, having a look at what we have. So based on all of this, we actually managed to create a cluster where people could on demand start training jobs and notebooks in a Kubernetes cluster. We introduced monitoring, and we had RBAC controls for our networking, multiple TLS. That was quite cool. At that time, the users were actually talking to the Kubernetes API directly. And so one thing that we found out is it's actually a bit complex for some users. Some users don't really want to know exactly how to build a Kubernetes manifest, and I would argue that that's fair. Another problem that we had is that we still were running on only one single cluster and wanted to find a way to kind of manage several clusters at a time and be able to spin up resources in different regions of the world. And lastly, we started by telling users to just create projects GitHub style. So again, create a YAML file, put it on GitHub. We will automatically create your project on Kubernetes. But we realized that many users weren't very happy with that, and they much better have a UI where they could just click a button and create a project and then start a TensorFlow job. OK, so here we were having one cluster. But imagine if you have several of them, 2 more, say, in Asia, in America. What we did is we built a small API layer and with a database with that. And that database will only have the notion of what is a user, a project, a resource, and a region, and would keep all the calls for auditing. And then we would have that API being able to communicate with all the different clusters around the world to spin up resources. And that API would become the single entry point for all of our users. Again, if we wanted to actually control and add some business logics about permissions from those API calls, we can use OPA. And one example would be if you want your projects by default to have GPUs disabled because you'd rather maybe contact the administrators to say, OK, this project is now allowed to use GPUs. GPUs are expensive on the cloud, so you might want to control that. You can actually bring your own business logic into OPA and filter those calls, which is very convenient. I mentioned about complex objects before. So this is an example on the right of it's actually a very simple pod that's running one script. And that pod is asking for a GPU, a K80 GPU in that use case. It's also trying to mount the file system I mentioned about. It's using an actual pull secret for a private repo. And it's asking for 16 gigs of RAM and 8 CPUs. This is actually quite big to write. And you can actually have a lot of mistakes in this if you miss the indentation of your limits or resources, or if you put them outside of your container spec. Kubernetes will not necessarily give you an error, but will not take that into account. And we had issues where people were actually wondering why their GPU would never come up, but that's because they put it in the wrong place. So what we did with this API is that we tried to also simplify how we spin up this. And on the left side, you can see exactly what a user was technically trying to do, which in this case, just run a script. Here's my image. Here's my script. And I want to run it on this type of node. OK, so now that we built this, we actually had a platform where we could spin up resources in different parts of the world, and we had a much better onboarding process. People were able to create projects and start a notebook in less than 20 seconds, and it made them very happy. This is a small example, actually, of a use case where, yeah, you can see you create a project, select the region, and give it a name. And for example, you want to spin up a Jupyter notebook. You can just use the UI to do this. So you can see some of the features that we have. You can choose the size as well, and you can speed it up. You see a small error. This is a screenshot from the dev cluster, so sometimes not as stable as we want it to be. But then you can just click connect to your notebooks and just start running. And one thing that I really wanted to stress is we built all of this using only projects like these ones that are open source, that are part of the cloud native ecosystem. And we were actually really surprised that we could go that far using these technologies alone. OK, so let's talk about some use cases. And actually, there's one which is very interesting, the clinical validation of our symptom checker. That was one of the biggest part of the work we did for the platform. So as I mentioned before, if you use the app and you tell them that you have a headache, for example, we have our symptom checker, which is a Bayesian network, and it actually has two jobs. The first thing is, based on what you are telling the symptom checker, it's going to try to get as much relevant information about you as possible. And then once it has enough information, it's going to try to come with an assessment, with an outcome. And if you want a nice equation, this is actually how it would look like. So give me the probability of a disease based on the evidence that I have. And we wanted to evaluate how well this model performs. And what the team has made, the team that's building this model, is they built a clinical validation process, and that would simulate interactions with patients. We had our doctors creating thousands of different use cases, and we're running this, evaluating both the questions asked by the symptom checker and also the outcome. And we wanted everything, every single use case, to be treated properly and also to be safe in the outcome that we would give. This was massive computing work, and it used to take 10 hours running on our on-prem servers, and that was very annoying for our developers and researchers. They basically had to spin up the job and then come back the next day, see if it failed or not. It made the whole feedback loop very, very slow. So what we did is we tried to encapsulate all of this, and we moved it to running on top of Kubernetes, and we used Argo for this. What we did is we optimized a bit the clinical validation code, and we also parallelized the API and model parts. We were actually using Argo to spin up as a daemon job about 16 or 20 different replicas of the model with the API. And what was really cool also with this is that since all of our production platforms run already on Docker, actually deploying this in the Docker container, the containers that we had here were exactly the same as we would potentially be deploying in production. So we were sure that this was the right version. So the artifact was exactly the same. And by parallelizing, we were actually going at first for a 50% reduction to 5 hours. But after a few weeks of work, we actually managed to take it down to 20 minutes. So really big parallelization. And now the team is working on actually putting this on every pull request. So every time you change anything to the model or to the code of the app, we get the feedback in actually now less than 20 minutes, which was a massive success for the team. And one good lesson that we learned, how if you improve the feedback loop, then you can actually enable so much more research. And at the end of the day, it also increases the safety of your model and also the quality, because you allow users to just try things and get results almost instantly. OK, so now what are we working on for the next steps? So the first thing that we really want to have is offering a common serving solutions to our users. Most of our developers are still figuring out how to serve their models, so mostly using TensorFlow serving. But some others, like the Bayesian network I talked about, they use their own kind of API wrapper around their models. So we want to kind of provide a common framework for that. And we're looking at KF serving, which is a very interesting tool on top of Knative. The second thing we want to do is to integrate with Kubeflow pipelines. Kubeflow pipelines runs on top of Argo, and it comes with additional features. But the most interesting part is you can actually code your pipelines in Python using their SDK, and then deploy it as an Argo workflow. We also want to improve the user experience. Everything on the platform runs on Docker, and it's still sometimes a bit annoying for users to actually have to build a Docker image, maybe run through some CI/CD, and then get it deployed, and then have it fail, and then having to reiterate. So we want to take that step away from them and build the image directly on the platform to improve the experience. And finally, we are adding more tools, actually, pretty much this year, around how to track all of our metadata centrally. And again, that's something where some teams are investigating different solutions. We are trying to find the best one to track all the models that we have in the company. And we're mostly looking at MLflow and Kubeflow metadata, which are very promising. OK, so I'm going to wrap up now. One thing I want to say is if you're looking to actually build a research platform on top of Kubernetes, I would actually argue that you found a really good platform for that. I think Kubernetes fits a lot of our use cases, and it was a pleasure to work with. And finally, well, Kubeflow is the best machine learning tool for Kubernetes that we've seen out there. It has a really great modularity, and was very easy to get started. You can just use kfctl to deploy it, and then once you get more comfortable with it, then you can play with customize and maybe only deploy the components that you're interested in. And for security and compliance, especially in our domain of healthcare or even in banking or finance, there's actually many open source out there, open source tools that you can use and contribute to. And that's something that we found while we were building this platform, is that you can actually get quite far with these tools. So if you want to have a look at this, I encourage you to go to the Landscape website and have a look around. And finally, for people kind of like with my profile, working more and more in MLOps, I think it's always come down to how can you enable your teams to be more efficient. Always try to keep that in mind. One thing that worked well for us was trying to talk to a team and say, okay, what is your biggest pain point right now? What can we do to help? And then focus on that pain point, build a small proof of concept, and if you see that it's working, then you can apply it broader in the company and serve more teams. And that's what we did for the clinical validation now. We are onboarding more teams to run their own clinical validation or cluster, and yeah, that's something that's working great for us. So if you find all of this interesting, I will be hanging around. Feel free to have a chat with me, or other people from Babylon are in the room. And yeah, so thank you very much, and we are hiring, by the way.
So we have time for about 5 minutes worth of questions, if there's any questions.
This was great. Are you donating or contributing anything back to the community after using so many projects?
So we did a few, we merged a few pull requests for Kubeflow. That's something that we want to do more and more. We were very limited in resources to build this platform at first, so now the team is getting bigger, and we'll have more time to actually contribute back. But yeah, if we can find a use case which is not there and that works for us, then yes, absolutely.
Yeah, thanks for the overview. Just kind of a quick question. How long did it take you to actually start putting this platform together and start seeing results?
All right, so we created this platform. So the proof of concept I mentioned before, like at the beginning, was last year. We started creating this platform in January, and by around February, March, we had our first users trying the training jobs and all of that. That was when the whole platform was only running on GitHub. So we ran a lot of workshops with researchers trying to understand what they needed. And the clinical validation part, we made it run about, I think, in April or June. And what was actually great is that the team now is actually managing this part. So we work with them, and now they are improving it more and more on themselves. So they have control over what runs. So they build their own UI and all of that, and it's actually quite cool. But yeah, I would say by summertime, we had a good enough platform, and then we spent the rest of the year running more security things and networking protection.
Cool. Well, thank you. Oh.
Did you guys do a lot of like CRD and sort of operator stuff around this, or did you sort of just glue it all together and have Argo doing most of the work?
So we did build some CRDs. So the project that I talked about, so the Kubeflow project actually has a lot of CRDs. So everything for notebooks and TensorFlow jobs, PyTorch jobs, Katib, all of that comes with CRDs already. But there are some additional tools, like for example, Wisdom or TensorBoard, where I think TensorBoard now there's a CRD in Kubeflow. But we built one for Wisdom, for example. It's okay to get started with CRD. I would encourage you, if you think like it's a good use case, to use CRDs. I think that's a good way to go. But yeah, so we do build a few.
All right, thank you.
Cool, thank you.